The topic of the presentation is about sequence without loops. If we consider our solar system, the best thing that ever happened to us and our blue planet is our lovely star, the sun. If you don't believe me, you can ask the sun itself, or these days, the oracle. Nobody get that one? So, for thousands of years, our ancestors have harnessed the power of the sun to improve their life. These days, we just take it for granted, thanks to, among others, Elon Musk. And it seems rather obvious that the source of our electricity should come from the sun. As everyone here in the Bay Area can witness, you can drive around in a car and spend $0 on the energy if you charge it through solar power. So, it's such a magical leap. Around 15 years ago, I bought the watch, and it's powered by this tiny little solar panel. And thanks to German engineering, it's still working right now, flawlessly. 15 years. That's what it takes for us to progress from a zero-cost watch to a zero-cost 4,000-pound vehicles. Now, let me flash back to a bit another moment earlier in our timeline. I was in my freshman year when I witnessed a very interesting solar energy engineering project. To remind you, this is the mid-90s, so newspaper is your major source of information. Your music collection is stored in a roll of magnetic tapes, and an alarm clock exists not in the form of a smartwatch or fitness tracker. So now, this is very interesting because that engineering project was a collaboration of undergrad students from different departments: physics, electrical engineering, astronomy, and mechanical engineering. The premise is very simple. If you look at the sun, the position of the sun during the day is not at a fixed location. So if you were about to build a solar system, ideally the solar panels would be flexible enough to track the position as it moves throughout the day to maximize its energy output. I don't have a picture for that, but imagine this solar panel mounted on a bulky and messy moving platform. You can think of it like R2-D2 with the solar panel slab on its head. The project itself was considered a success. However, the team realized that by building this optimal solar panel, flexible solar panel that tried to get the maximum ounce of power possible, at the end of the day, remember this is mid-90s, that's all the power that it gets. So it's just barely enough to move the motor and power its electronic system. In other words, if this entire machinery is not sustainable in a sense that it cannot even sustain its own power consumption, it won't have enough energy to charge your Tesla. In that way, the project is not necessarily successful, but the team members of the project later went to build a very much successful product unquestionably influenced by whatever experience that they've been through. So, if you consider the state of web development these days, I think from time to time we need to carry out such a perspective reset. What if you're not worried about another transpiler, another virtual DOM, another this, another that? What if you're not constrained by the fact that whatever solution that you're building right now won't make it into the production? What if you're not forbidden to build a solution looking for a problem? What if you know that whatever you're experimenting right now is going to go down the drain, but you're still having fun and learn new things while you're doing it? This talk is about that. This is about experimentation and exploration. It's not about the most optimum possible code that you can squeeze out of a certain operation. It's not the most pragmatic best practice and code patterns. It's not about this is what we need to deliver today. It's all about having fun. So the only constraint that we will impose on ourselves for this particular subject is that we will not use any loops. And by loops here means the normal for loops, or when it's represented as a do-while. So I'm sure some of you will ask about this, so this is a warning for anyone that asks about performance of all the code snippet given here. So without further ado, let's start with the first topic. What if you want to create a sequence using JavaScript? This is a programming 101. If you just want to build a list, an array of number, 1, 2, 3. This is the most obvious thing in the world that you will do. Create a for loop, push the numbers into an array, big deal. Same, if you want to build a sequence of characters, this is the way you do it. You leverage the built-in string from car code function. Now, here's the challenge. How can we do this without any loops? Without for, without while, without do?
Map.
Hold on. Don't spoil it for the rest of us. So let's start by creating an array. So fantastically, there's this built-in object called array. What if we just, array 3 and then assign it to a variable? Anyone can tell me what's going to happen with x? Well, first of all, the length property of that x will be 3. Rightfully so, because we just said, build an array with 3 elements. But if you try to console log it, then you're just going to get square brackets, nothing inside. Which comes me serious. Don't you think that this should have some default value so that at least it's going to show 3 elements? Why this array is empty? So when I put some labels there, that's the reference in the ECMAScript 5.1 specification. If you are crazy enough to read the spec, feel free to go to that section. If you use the operator in to detect whether certain elements exist in an array, you will see that all in array 3 is false. So the first element doesn't exist. 1 in array 3 is also false. 2 in array 3 is also false. So it doesn't exist at all. It's as if this array is full of ghost element. You can test that the operator in works correctly, because if you just put 2 in, square bracket, comma, comma, 9, it says true, because there's third element there. So the reason in the previous slide that x is empty is because the console of x is empty is because it will call x to string, and because it's an array, to string is trying to do a join on the entire element, and join, if it sees undefined or null, it's going to convert it into empty string. Hence why the result is just square brackets with nothing inside it. Already confused? Welcome to JavaScript.
Does it do that in every browser?
Yes. So, well, fortunately we have apply. So we can do this, write apply 0, write 3, and then if you console log it, then you get undefined, undefined, undefined. It's still useless, it's undefined, but at least you get something. This is one milestone that we achieved by doing this. Just a reminder, if you're not familiar with apply, if you have a bunch of numbers and you try to find the maximum numbers, you can use math.max. But if your numbers is an array, then there's this technique using apply that's technically called spreading. So you use apply of that math object on that array will turn into a series of function parameters. So those two lines are the same, but as you can see in the first line, you can pass an array. In the second line, you need to pass the numbers as parameters. So apply does this trick, but it's still undefined. So the next step is that, in the case of apply, fortunately, unlike join, or toString as well, if apply sees a construct like this, it's going to turn everything into undefined. So here's map to the rescue. Map will, how many people are here using map? Alright, map. Okay, so you know what it is, I don't need to explain it. Here's a simple example of map. We just produce an array of square numbers. X is the element, and then you return the value that is the square of that X or element. You could also utilize the second parameters, which is the index of that element. So in this case, if I put 777 and map, I'll take only y, I'll get 0, 1, 2, 3, 0, 1, 2. So here's the trick. We can completely ignore the value and just use the index. And that's what's going to happen. So if you do the first line, the result is 3 times undefined, but if you do the second code snippet, you'll get 1, 2, 3. Because we don't really care about x, we just want to use y. And if you do this, the last example, then you get those square of those indexes. Make sense? So with this, you can build a sequence of number without using anything, just relying on apply and what was that? Yeah, map. The slide deck is almost online, so and there's a lot of resources out there that I'll point out throughout the deck. if you want to understand this on your own time. Same with string. Here we use array constructor to produce an array of undefined and use map to turn it into an index, and then we use the usual conversion to string to be able to construct a list of characters. That blog post will explain everything in details. I see that everyone is confused. You would expect functional programming, right? Instead you get this mumbo jumbo. So in order to make sure that you're not falling asleep, I will put a little bit of pop quiz. So this is like a mess, aka chaos, but somebody says that every great change is preceded by chaos. Anyone else who said that? I don't know. Hemingway, Sun Tzu, George Bush. I'm disappointed, guys. It's from Deepak Chopra. Okay, next topic. What if you want to produce a list of prime numbers? Let's up the challenge a little bit. So we already have a sequence of numbers. Now, how do we produce a list of prime numbers? Let's start with basics. How do we know if a number is prime or not? We can use this test. Basically, we create a loop and we check whether that number is divisible by our index. Can we divide I by C? And if the answer is no, you cannot divide that by anything, then it's prime numbers. Here's an example. How do you know that 23 is prime numbers? Well, you take square root, it's 4 point yada yada, just take 4, create a loop from 1 to 4, you don't need 1, go straight to 2, 2, 3, 4. If you try to find the modulus or the remainder, well, it's not 0. In other words, you cannot divide 23 by 2, by 3, by 4. And therefore, it's a prime number. Different example, 27 is not a prime number because as you loop through from 2 to 5, boom, when you try to divide 27 by 3, it works, the remainder is 0, and therefore this is not a prime number. Again, we have loops. That's all we want to leverage here. But we need to iterate through that and stop at some point. Anyone can guess which array higher function we want to use here? Let me quickly give an example. This is the classic loop way to build a prime number. So you just loop through from 2 to something, call the function is prime. If it's prime, then push it to the list. But we know that loops are overrated one. We don't use loops because our loops are from loops. So we can use every. Anyone here is using every on a daily basis? Yes. The nice thing about every is that it's going to stop at some point. So that's the magical thing that we want to exploit here. An example, if you try to find, try to form a conditional age greater than or equal than 18, and one of your numbers inside your array is 17, it's going to stop right away after it hits 17 and say it's false. But looking at the second example, none of those numbers, or every numbers in that array is greater than 5. So it's going to continue until the end of the list, the array, and say true. I cannot find something that doesn't fulfill this condition. So that's our trick. This looks complicated, but this is all it takes to find whether I is prime number or not without any loops. You do the usual apply thing, and there's this trick, double tilde there. That's just the equivalent of math floor. I'm just going to try to obfuscate the code a little bit. But you can try with math floor of math square root and figure out that it's working. And then after that, once we already have the sequence, we run every to that. And then do the check. The I modulus y is that particular check. Can we define I by y? So you look through from all numbers from 2 until some limit, and then if every doesn't complain about everything, for every variable in that loop, obviously that is prime number. So now we can try to take advantage of filter, because remember the objective is not to check whether the number is prime or not. The objective, please produce the list of prime numbers. So there's another loop that we need to do. And filter is fantastic here because filter will not stop. Filter will check every single element in that array and then pick the one that fulfills the condition. Here's an example. If you have a number like that in the first code, our condition is it has to be positive or a 0. And therefore, the one that we produce, the one that is returned by filter is all the positive numbers or zeros. Same with the next example, it has to be odd numbers. So, here it is. This 4 lines of code. You can put it in one line if your line is very long. That's all it takes to produce a prime number, a list of prime number up to n. Questions? So again, it's very easy to analyze this. This is the outer loop, and the inner loop is the one that I've shown before. So for a lot of purists, this style of functional programming is breaking the rules a little bit because you're not supposed to do that. But I like this quote: learn the rules like a pro so you can break them like an artist. Who said that? Picasso. We're getting better. Yes, this is our friend Pablo. Any question before I move on to the next subject? I got a question. Yes.
Who says that's, what's the thinking if that's not the right way to do functional programming? You mentioned that there's some naysayers on this stuff.
Let's talk about that offline, because this will disrupt the flow a little bit. You will see that this is just actually preamble to a much more rule breaking that we're going to introduce very soon. So I tried to set the expectation that it's okay to break the rules. Computing factorials. So this is getting much more interesting. What is factorial? So if you have n, it essentially multiplies all the numbers from 1 until n. So factorial 5 is 120 because 1 times 2 times 3 times 4 times 5 is 120. This is the traditional way to implement factorials. In other words, you just look through all the index and then multiply them. Pretty straightforward, no big deal. In order to implement this using arrays higher order function, we have to take advantage of reduce. So reduce is a bit complicated, and this is where we start to break rules like a madman. How many of you here are using reduce? Well, that's actually more people than every. It's interesting because reduce is the most generic form of all this array higher order function. Here's an example. So you can build accumulator this way because you can just keep adding numbers, like in the first example. One of the advantages of reduce is you can have initial values. So if you try to sum 1, 2, 3, 4, 5, but you want to start with 100, you could do that. You just pass the initial values to reduce. Even better, reduce can accept anything, any object. It can accept an array as the initial variables, and then in the last example, you just keep putting more numbers into that array. So concat is not magical. If result is an array, concat something means just put this as the last element in the array. So now you can start to see how we're going to produce factorials. It's actually even simpler than the previous example because that's all. If you see, you're already familiar with the array apply. That's just to loop. And then the next one is a bit magical, but the purpose of that is to accumulate numbers. And probably easier to explain using this chart. So if x is the value, y is the index, we ignore that, and z is the initial value. So we start with z like this. This is how you progress through x and adding more values into the array. If you see 24 there, it's produced because you multiply 6 with 3, x times z is 18 added to 6, that's 24. So essentially we take advantage of reduce, or rather abuse reduce to act as an accumulator. That way we get factorials. We can just keep multiplying numbers. Questions?
Is the recursive method considered just a form of looping in, or because this could be done with that?
This could be done with recursive, yes. But I'm supposed to talk about functional programming and recursive programming. That's okay. I'm not trying to give you a hard time.
I don't quite understand how this slide is supposed to work.
Oh,
it's just important.
Yes. This is only to expand this while there's x plus x plus x plus x multiplied by z. That's the accumulator trick.
Yeah, but if you multiply by 0, you would get 0.
Yeah, but look at the initial value as well. Ah, you missed that.
No, I know, but in this next slide is space 0 in C.
Yeah, that's a bug. Thank you for pointing that. So, anything to be concerned of before we go into my favorite topic, rabbits? Cool. There's this man, some Italian named Leonardo Fibonacci, that sort of coming up with a mash-up of biology and mathematics and produced this Fibonacci numbers or series. It's about rabbit population, and it works like this. So it starts with 0 and 1, and you can know the next number in Fibonacci series just by adding the two previous numbers. So in this case, if it's 13, it's 13 because the previous number are 5 and 8, and you just add them, and you get 13. So here's the classic way to do Fibonacci numbers. If you ever ask this question in an interview, you build a loop, and since for any index it depends on the two previous number, obviously for the first two numbers we cannot add the two previous number because they don't exist yet. So that's why there's this complicated ternary operator in the middle. Basically it's just as in the beginning just use 0 and 1. That's the initial starting point. But after that, just add the two previous numbers. So if you call this function like this, Fibo5, you get 0, 1, 1, 1, 2, 3, 5, 8, and so on and so forth. So how do we do this without any loops? Still pretty simple. In this case, we use reduce, but our initial value is an array because we want to produce that Fibonacci series in an array. Again, we abuse reduce and implement something very similar to the previous loop. We add new number to our array. That's the next number in the Fibonacci series. And if it's the first two elements, just put 0 and 1. If not, then keep adding the two previous numbers. This one illustrates that. So for the first time, when we still don't have anything in the array, which is x, then you just put whatever we have as the index, 0 and 1. Because for Fibonacci series, you always need to start with two numbers. And then after that, well, that's easy because you just pick the two previous number and add them, and that's the new number. This way, again, it's like accumulator, but you rely on not only the current index, but you rely more on what were the two previous values in that array. This way you can grow the rabbits like Fibonacci intended to be. So if you want to know more about all this craziness, prime numbers, factorials, and Fibonacci series with array, refer to this blog post. Oh, there's no pop quiz here, but the last one. So once you already mastered this, some of you might ask, well, why this complicated dance to do this, right? What's the point of all this madness? Well, creating sequence and trying to test for conditional, that's very useful because, for example, you can do searching. Searching essentially looping through some elements and try to find what you want. I've given a detailed explanation about searching both using sum and reduce. Again, this is done using any loops. Another, for example, here's a good example. If you want to find, if you're given an array of strings and you want to find the longest string in that array, yes, you could do that with loops, and you could have a very nice code that does that, and then you can test that. But here's the more functional style of doing that. So essentially, we loop from one element to another, and every time we find a string that is longer than our what we have, then we just going to replace it. And by doing that, we can also produce the index. So in this example, A, B, A, B, C, and A, the outcome of this function is, of course, the longest is ABC, but it's also going to say that the index is 1, because this ABC is the second string in that array. So feel free to refer to this for further details. Once you get into searching, then you can do sorting, because that's the ultimate computer science problem or interview question that we're going to have. Here's this entire function to sort an array of numbers without any loops. And if you look at it, this is actually simpler than implementing any kind of quick sort that is prone to error or bubble sort that is extremely slow. What do we do here? We search for the smallest number or the biggest number, depending on your ascending order, and then add it into the result. So essentially, there are two loops here. The first loop is just looping through elements. The other one is what is the biggest number that we have right now, and then sort it.
That's like bubble sort.
It is. So this blog post, the second blog post, illustrates the explanation or the magic behind it. There's also something called sorting networks. This is probably popular among hardware engineers because you can implement sorting with hardware, and therefore you can take advantage of parallelism. But this is the simplest example of sorting without any loops. Okay, don't worry, I'm getting there. So in this example, without realizing it, you actually see a couple of arrays higher order function in action. Map and filter that always return a new array, and it will visit every element. Reduce is the same thing. Reduce can accept initial value, and that could be a primitive object, numbers, string, what you have, whatever it is, or a much more complex object, an array. And reduce is the one that I typically abuse a lot. And every and some, that is useful for searching because there are conditional involved with that, and depending on how you write the conditional, reduce or every or some will stop at some point. And it's just written a boolean, so you don't get any meaningful information out of that. Map filter reduce sum and every, and you can use the combination of this function to look for prime numbers, build a list of prime numbers, compute factorials, coming up with Fibonacci series, and you can use every sum reduce to do searching, and ultimately combining all of this, you can implement sorting. So, if you're afraid to touch higher order function, don't be afraid to try to take advantage of that. They're very, very cool, and they're a very nice way to get into functional programming. And hopefully we really put functional programming and functional programming, not dysfunctional. I promise you, last question. When I don't know what happened, it just bothers me, get under my skin, and I need to write about it. This is
Taylor Swift.
This is something that I learned from investigating or researching this topic. Anyone knows who said that? Who reads their Hemingway? Nobody believes that this is Hemingway. Yeah, this is Taylor Swift.
I was waiting for it.
Of course you are. So, thank you very much.
Thank you, Ariya, for teaching us that what Taylor Swift and rabbits have in common is functional programming. For those who don't know Ariya, he wrote Esprima and PhantomJS, so probably the vast majority of you are benefiting from his hard work. Next up, yeah.